Okay, in this next lesson we're going to be talking about solids of revolution, and basically we're going to be doing volume. We're going to work on the disk and washer methods today, but the first one is the volume of a disk, and we're going to look at our Rx region. So we have our definition here, and I'll let you pause it for a second and read through that. But basically it's our limit of pi times the f of w sub k squared delta x sub k. And I kind of put down here exactly what those represent. So that's the area of the disk. That's what we've done previously in a previous lesson. And this represents the thickness. So it's represented by this interval over here. And if we look at that, the images down here, we can see that we're going to, this is the 3D version of it, or the attempted 3D version of it, that this is your f of w sub k here. This is w sub k. So if I select this particular disk and my axis of revolution, we're going to revolve it about the x-axis. You can see that if I have this image and I look at this particular dx, this disk, and I'm willing to revolve it around the x-axis, we'll have a figure like this. So this, and we can find the volume of that. Okay, so if we were looking at the RY region of a disk, we may have a figure, and the intervals change from C to D. Remember, because we're going to be on the y-axis here, so our intervals are from C to D. If I pick this particular area for a disk, and in this case it represents here, then you can see how these adjustments are made to reflect the RY region. Where this is going to be the area and this is your thickness. And you can kind of see that extended. The general rule for finding volume of a disk, of a circular disk, would be pi times the radius squared times the thickness. That's our basic rule for volume. So here we can see the axis of revolution. If I have one particular disk, I was finding the radius is here, the thickness would be here. So we extend that to the RY regions as well as the RX region. In this case, the area of the disk squared times the thickness. So we could see that comes from this value here. Okay, after giving our formulas, the first thing they're going to ask us to do is just to set up an integral to find volume. Now they give me this equation, y equals 1/2 x squared plus 1, and I went ahead and sketched that graph for that into the x-axis, and then we're going to revolve that around the x-axis. Okay. So we have our formula down. So I have volume is equal to our intervals. What's our a to b? We're writing everything in terms of x. So what's the x values? Very good. -1 to 2. Okay, and that's from here, -1 to 2. And then we just have pi. And it's okay if I pull pi out front because pi is just a number. I'm actually going to scoot this over so I have a little more room. Volume. It's common that we'll pull pi out front. Now what's f of x in our particular case? Yes, it's given to us, so it's 1/2 x squared plus 1. And then what do we want to do to that? Square it. And then we have dx. Okay? And that's all they ask us to do in this particular case. Okay, so our next one, we're going to actually set it up and then find the volume. In this particular case, they give us two equations. They give us y equals -2x squared plus 2. Like you said, you can use your graphing calculator to sketch these out or make an xy table, just graph these. Y equals -x squared plus 1. It's revolving about the x-axis. Okay, so we're going to set this up. So our volume is equal to, let's pull the pi out. What's our intervals going to be? Now, to get these, we can set these two equal to each other and solve algebraically, or you can do the intersection in your calculator, whichever's better for you. So I'm going to pause it and do that on the side. Okay, algebraically we get x is plus or minus 1, so we're going to have our intervals there. Okay, in this particular case, I don't have a green, but we're going to do the top function and we're going to subtract out the bottom one. So how will we represent that? So it's going to be negative 2x squared plus 2 squared minus negative x squared plus 1 squared. Let me put all of that and then times dx. Which we're going to back up for just a second, and I want you to see this formula because this is what we just did. We were given two functions, an f of x function and a g of x function, and I missed this somehow. It's a little bit out of order, so if you, in your notes you want to make a comment about it. If I'm given an f of x function, a blue, and a g of x function, then you're just going to take the f of x function squared minus the g of x function squared dx, which that's what we just did in this example right here. This was our f of x, and then we need to take this formula right here. And we want to change. So f of x squared minus g of x squared right here. So this is f of x squared minus g of x squared because we have two functions, dx. Right? Where in the first case, we had just that one function and then we were going to the x-axis. When you're given two functions, the only difference is you're going to have the functions subtracted out right there. Both still squared dx. Okay, also we could use our symmetry rules because you can see that if I was to fold this right here, it would be exactly the same. So I want you to try to set this up using symmetry. Good, so we have 2 because we're only going to evaluate this part. So from 0 to 1, right, because we'll get the area of this piece and then multiply by 2. So bring your pi out, and then this portion, your f of x minus your g of x squared, will still be the same. So it could be represented either way. One's using symmetry, the other one's not. Okay, so the first two, we just set them up. The next example, we're going to actually find the volume of the equation. You're going to be given this information, and you're going to be asked to draw the sketch. So I've provided the sketch for you just for the sake of time and not having to draw it out, but basically you can graph these in your graphing calculator or making an XY table. Revolve this about the x-axis. Okay, so take a few minutes, make your sketch. This is what a 3D sketch was if we chose the disk and then revolved it about the x-axis, just so you have a little bit of a visual. The textbook does a much better job with the visuals, so if you want to refer to that, you may. So then, first of all, just set up your integral and let's check your work. Now, when this is about the x-axis, my axis of revolution is here. My dx representative rectangle that I draw is perpendicular to the axis of revolution. And we're going to talk about that a little more because you can see with disk and washer method, it's going to be perpendicular to the axis of revolution. And we're going to learn about another method, the shell method, where it's parallel to the axis of revolution. Okay, so when we're setting up, our interval is going to be from -4 to +4, and you can check these values in your table or plug in when your x is equal to 4, you'll get y is equal to 0, so that's this ordered pair right here. Okay, so we can see that it's going to be -4 to 4. And I'm going to pull that pi out front. And our f of x is going to be square root of 4 minus x squared dx. So let's look back at that. Square root of 4 minus x dx, that's our function, squared dx. Now let's simplify this before we start. What is the square of a square root? Algebraically right here. Good, right? We just get pi -4, 4, and that just gives us 4 minus x dx. Now let's go ahead and calculate this. So take the antiderivative, so we just have our pi. What's the antiderivative of this term? 4x. What's the antiderivative of just x? X squared divided by 2, or that's just going to be 1/2. Evaluate it from -4 to 4. Okay, so I'm going to pause this. We're going to plug that in using the fundamental theorem of calculus and calculate the answer. Okay, so you want to check your work here. Remember, you're going to evaluate this. So this is the antiderivative is 4x minus x squared divided by 2. Evaluate it from -4 to 4. Plug in 4. Subtract when we plug in -4. Simplify this, and we should get 100.53 units cubed.